to all students. وعليكم السلام. Let me begin this session for you. In this session, we see some basic properties for Banach algebra. We see the definition of Banach algebra in previous sessions, and in this session we see some properties for Banach algebras. At the first, let me express these definitions. Let A be a unital algebra so that we have an identity. Okay, unital algebra. An element A in A is called invertible if there exists an element such as B with these properties. We must have these equalities. AB equal to BA equal to the identity element of A. The element B is unique and it is called the inverse of A, and written the inverse of A. Okay, and the set of invertible element of A is denoted by inv A. The set of all invertible element of A. It is not that it is very trivial that the inverse element must be unique. Okay, the inverse element must be unique. For example, let A be an unital algebra and A in A is invertible or B invertible, then the inverse of A is unique. Because if B and C are inverse for A, then B equal to BE. Okay, and this is equal to B AC. BAC. Because B and C both are the inverse of A, so that BA equal to AB equal to E, and also CA equal to AC equal to E. We have all of these equalities, so that we can consider E equal to AC. Okay, E equal to AC. But by associativity, this equal to BA multiplied by C, and BA equal to E again, so that this is equal to EC and this is equal to C, so that this B must be equal to C. Okay, and the inverse of any element in any unital algebra is unit. Dear students, do you have my voice? Mrs. Layla and Mr. Sajjad, do you have my voice? Mr. Sajjad, do you have my voice? Okay. And the set of all invertible elements of A is denoted by this notation in A. Okay. Check that if A and B belong to the set of all invertible element of A, then AB is an invertible too, and we have this equality, and this is trivial because if A and B belong to invertible element of A, we see that AB multiplied by this element, because we have the inverse of B and we have the inverse of A. This is equal to A, B inverse B, A, and this is equal to identity, so that this is equal to this, so that is A inverse. This is A inverse. And this is equal to A inverse, and this is equal to identity map. So that this must be the inverse of this element. B inverse A inverse must be the inverse of AB. We know that the inverse of elements are unique. We proved this, okay? Similarly, we have this. The multiplication of so that this must be the inverse of this element, and this is the proof of this statement. And also for any unital Banach algebra such that equal the of this, and this is less than or equal the norm of A multiplied by the norm of A, and this is equal to the norm of A to the power of 2, because we know that in any Banach algebra we have this inequality. Okay, we have this inequality. We can continue with the cube of A equal to A2 multiplied by A, and this is less than or equal this norm multiplied by this norm. But the norm of A2 is less than or equal the norm of A to the power of 2. So that this is less than or equal the norm of A to the power of 2 multiplied by the norm of A, and this is equal to the norm of A to the power of 3. And inductively we have this inequality for any n in natural numbers. Okay, and as a consequence, this is less than or equal this, and this is equal to the norm of A, so that for any n in natural numbers we have this, and this shows that in this set all elements are less than or equal this element, so that the infimum of this set is less than or equal the norm of A. Okay, the infimum of this set is less than or equal the norm of A. But for these equalities, please note that we have these properties that the infimum of a set such as this equal to an element alpha if and only if we have two properties. One, for any x in all set, we have this property, or alpha be in lower bound for A, alpha is a lower bound, and 2. For any epsilon, there exists an element of A such that x is less than or equal alpha plus epsilon. And this is very trivial because the infimum of A is the greatest lower bound, so that any elements created that alpha cannot be a lower bound, cannot be a lower bound, or we have not this property because this is the greatest lower bound. We don't have this property that for any x in A we have this property. The negation of this must be whole, and this is equal to this. There exists an element such that we have the negation of this, or we have this property. So this can be considered strictly. Okay? Okay? This is a known fact about infimum, and we have a similar properties for the supremum. Okay? Now we want to prove this property that we want to prove this property that the limit of this equal to the infimum of this set. For its proof, let's we consider alpha equal to the infimum of this set. Okay, this is our set A, for example. Okay, we consider alpha equal to the infimum of this set. Then for each non-negative epsilon, we must have an element of this set that exists a natural number such as n this is less than 1. Now for each n greater or equal n, by the algorithm of division, we have n1 and r, for example, with this property such that n equal to n1 n plus r. Actually, we divide n to n1, n to capital N, okay? So we have these two elements. So we see that this equal to a to the power of n1 n plus r by this power, and this is equal to a n1 n multiplied by a r by this power. and this is equal to or less than or equal, okay? This to the power of 1 divided by n, and an by this power n1 n. It is very trivial because we have in a Banach algebras, and so we have these properties, okay? But this is less than or equal the last one is less than or equal the maximum of 1, the norm of A, the norm of A2, and finally the norm of A by this power then this power, and we know that the norm of an is less than or equal the norm of this to the power of n, to the power of n, so that this is less than or equal alpha plus epsilon by this power n, n1, n. It is very trivial because this R is an element between 0 and this, okay? So that AR is less than 1, A1, 2 up to the A by this power, so that this is less than or equal this maximum, because this is n is one element of this set. This is one element of this set, so that this is less than or equal this maximum, and we repeat this power into a statement, okay? But it is trivial that it is a fixed real number. It is a fixed real number, okay? Please note that. It is a fixed real number, such as beta, for example, okay? If we denoted this by beta, beta by this power 10 to 1, okay? this 10 to 1, and this equal to n n1 divided by n equal to because we know that n1n equal to n minus r, okay? Alpha plus epsilon n minus r divided by n, and this is equal to alpha plus epsilon 1 minus r divided by n, and this 10 to alpha plus epsilon. If n tend to infinity, this 10 to alpha plus epsilon is 10 to 1, okay? So that this is less than or equal alpha plus epsilon. Okay? Or we can write 10 to alpha plus epsilon. By these two reasons, this 10 to 1 and this 10 to alpha plus epsilon, so that this multiplication 10 to alpha plus epsilon. This shows that for any non-negative epsilon, the limit supremum of this set is less than or equal alpha plus epsilon for any epsilon. Therefore, we have this inequality. Since this holds for any epsilon, this is must be less than or equal alpha. Since this is holds for any epsilon, you can turn epsilon to the 0, and we have this inequality. Okay? This implies that yes, if we consider alpha limit infimum of this set, we know that this limit infimum is less than or equal limit supremum, because limit infimum always is less than or equal limit supremum. Okay, and we prove that this limit supremum is less than or equal alpha. This shows that the limit infimum of this set equal to the limit supremum of this set. And finally, and we denoted this by alpha, this shows that this limit must be alpha. This limit must be alpha. You know that the limit of n sequence, okay, equal to alpha if and only if the limit infimum of this sequence equal to the limit supremum of this sequence equal to alpha. If the limit supremum and limit infimum equal, then this sequence have a limit. Mr. Sajjad, do you have any question? Okay. Mr. Sajjad, we can continue in the next session because we have been Ramadan. Okay. Okay.
بالنظر إلى أننا نقترب من الإفطار، سأواصل بقية المحتوى في الجلسة القادمة.
Inshallah. And
أهنئكم بعيد الفطر مقدما.
شكرا لك. Thank you very much and goodbye for now.